very much. It's a real privilege. It's a real privilege for me to be here. Astrophysicists scale very, very high heights, unimaginably high heights, but they don't use their hands and feet. They use state-of-the-art telescopes to peer into the cosmos. It's a sort of metaphorical peering, of course, and then we try to understand what we see in the cosmos using the physics that we have learned here on Earth. And given the fact that the sky is actually a universal laboratory, astrophysics can lead everyone along this path of understanding. So, as you perhaps know, for most people, the beginnings are very early. For me, the beginnings were over half a century ago, when my parents had the habit of spreading a mat on our garden after dinner and we would watch the sky at night. I would love to spot the planets in the sky, even more to spot a meteor, which was of course occasional. Once a comet appeared and it spread its wide and long tail across the sky. It was really fascinating. And I remember vividly drawing a painting of it from things which form or which exist in some of in the earlier phases of the life of the universe. So one of the things that used to fascinate me in those moments on the mat in our garden was on a clear night when one could spot the Milky Way. Tenuous, very, very tenuous, but nevertheless breathtaking. And although the Milky Way appears to us as extremely serene and breathtaking, that feeling, as you know, is deceptive, right? Because each one of those little points of light is a star like our own sun, a boiling cauldron with very, very energetic processes happening around them. So the tools that astrophysics uses came to me in a sort of a chaotic way, I should say. Real tools, imagination, fantasy, all mixed in. I was born a year after Sputnik was launched. So the first humans in space, Yuri Gagarin and Valentina Tereshkova, were my childhood heroes, and I fantasized about being a scientist on a spaceship. When I was about 8 years old, my parents got me this really beautifully illustrative book called The Atom. It was a children's book. And in it was a description, an illustrated description of the famous Rutherford's gold foil experiment, where Rutherford stretched this foil of gold and bombarded it with very energetic particles. And given the picture they had of the atom at the time, he expected that all these particles would go through the foil. But what he found was some of them actually bounced back. And this really changed how people thought about atoms. They realized that most of the mass of the atom is actually concentrated in the center, which is what caused Rutherford's energetic particles to bounce back. And that experiment really floored me. I thought it was so cool, but it also, sort of looking back, brought to me what the scientific method was. How it was about the refusal to accept anything without testing or trial, and the willingness to change our previous conclusions in the face of new evidence, as Jawaharlal Nehru very evocatively said a long time ago. And the other tool that astrophysicists use, which also made its way into my brain at the time, was of course mathematics. And we learn maths in school, obviously, but my parents got me these books of mathematics written by Walter Sawyer, which gave me a very intuitive understanding of what mathematics was. For example, it gave a glimpse as to why mathematics is such a beautiful language for us to understand nature with. The Milky Way, it stretches like a band across the sky. But that is because the sun and the solar system and us, we are part of this Milky Way. And so by looking and measuring how all these stars move in the Milky Way, we now know that it forms a swirling mass, a swirling spiral mass of stars. But perhaps the most surprising thing about our Milky Way is something that I never imagined, of course, was possible while I was watching it as a child, is that at the center has been found a really massive, giant black hole. So it was a discovery that was a result of a quest based on suspicions that were building up over a very long time. So just to remind you about black holes, one can get an intuitive understanding of black holes using the kind of high school physics and the idea of escape speed that many of you probably just learned about. So you know that if you throw something from the surface of the earth, it will land back on the earth. You throw it faster, it will go further but still land back. But there will come a speed when the thing that you launch will escape the earth, and we call that the escape speed. And for the earth, it is about 11 kilometers a second. Now suppose you do a thought experiment and take all of the mass of the earth and squeeze it down. What happens is the mass remains the same, but the distance from the surface of the earth reduces, and therefore the escape speed increases. Now if you continue this thought experiment and squeeze it so much, squeeze all of the mass of the earth so much, that the speed, the escape speed, becomes the speed of light, which is 300,000 kilometers a second. Then we know that light is the fastest thing that's possible, and so therefore nothing can escape from that thing. It turns out that we need to squeeze the earth to, that is all of the mass of the earth, to the size of about a marble, in order for nothing to escape from it, or in order for it to become a black hole. Now you might say that's impossible, and that's probably true, but if you do the math, it turns out that the bigger the mass, the less of a squeeze it seems. So while the earth has to be compressed to marble size, which seems a little impossible, the sun, in order to make it into a black hole, needs to be compressed to the size of about 6 kilometers diameter. So that's a bit less of a squeeze. And if you think of Gargantua, which is a fictitious black hole in the movie Interstellar, that was given a mass of 100 million times the mass of our sun. So that was much less of a squeeze to make it into a black hole. So what we do not normally learn in our high school physics is Einstein's new way of understanding gravity. Not as a force between two things, but instead as a thing that masses do to the fabric in which we all sit. So the way John Wheeler described Einstein's theory is very evocative. He described it as masses tell space-time how to curve. So the more the mass, the more the curvature of this space-time. And that curvature tells things how to move. So therefore, light follows the curvature of space-time, and therefore clocks tick slower, close to massive things. So let's come back to the center of our Milky Way, where I said a very, very big black hole had been discovered. So this was a suspicion that was building for a long time. And in round about 1995, scientists had access to enormous telescopes that could capture light in the infrared. And that was necessary in order to penetrate the sort of dusty fog that is there in the center of our Milky Way. And so what they did was image stars in the center of our Milky Way and take snapshots of these stars at different time intervals to see how the stars move and thereby determine their speeds. So what you see here, the multicolored splotches that you see here, are real stars. And on the top, the date at which the snapshot was taken is shown. And what you can see is that these stars are moving. And what the scientists found, which is also what you can see, is that the stars are not moving randomly. They're not moving in straight lines. They're moving in elliptical paths, and all these ellipses are around the same focus, very reminiscent of our solar system, which suggests that there must be a really massive something that is driving all these things in these elliptical orbits. Furthermore, the star which approaches that focus closest goes along, approaches closely, and then continues on its elliptical path, which means that this dark thing which is driving all these stars in elliptical orbits must be smaller than the closest approach. And if one does the maths, it turns out that there must be a 4 million solar mass black hole at that spot, which is the center of our Milky Way. Now, another group of scientists used a completely different method to image that same region. As we saw in the fictitious Gargantua in Interstellar, if stuff comes near a black hole, it gets drawn to the black hole, of course, but in the process it gets heavily accelerated, heated up, and due to that, it starts to glow. So although the black hole itself is black, and one can't see it, stuff around that black hole glows very, very brightly. And so it is possible to capture the silhouette of that black hole. And this is what the second group of scientists did, and that is what you see there on the top left corner. The fascinating thing is that what they saw, this silhouette of the black hole, was not only consistent with what the other group of scientists measured using the movement of the stars, but it was also consistent with the computer simulations that showed what happens to stuff that swirls around the black hole and starts to glow. So all of these different methods gave the same result. And that is the power of science. So science is about constantly testing our conclusions. Two different groups use the same method of stellar orbits in order to determine the mass of the dark black hole. And they found consistent results with each other. And then there was the completely different method, trying to measure the silhouette of the black hole, which also gave consistent results. And then we put all our understanding, physics understanding, into a computer simulation and see what comes out of there. And that was also consistent. So that is the power of science, the power of questioning constantly. It turns out that not only does our Milky Way harbor a giant black hole in its center, but there is a giant black hole in every galaxy that we've looked at. And the swirling mass that glows gets so heated that it all becomes ionized and generates magnetic fields, because of which some of that material does not plunge into the black hole, but is instead squirted out in giant jets of plasma out into intergalactic space. And this has, when you zoom in right into the center, we actually see this happening, as is seen on the left. And when we do computer simulations to ask the question, is this physically possible given our physics understanding? There too, the answer is yes. So on the right is shown a computer simulation, and the green lines are the magnetic field lines, and it shows you how they sort of get into this twisted configuration, as a result of which some of the stuff is launched out away from the black hole into intergalactic space rather than plunging into the black hole. And this particular galaxy, if we're talking about scaling heights into the future, especially for the younger generation, it has to be about honing our skills in questioning everything around us. Remember I said that as a child growing up, I could see the Milky Way, even though I was growing up in a relatively medium-sized town. Nowadays that is out of question. So you, the next generation, the stewards of our planet, need to bring back the Milky Way for your children. So we need to bring scientific thinking into our everyday practice. We need to remember the words of Gandhiji, who said, "The earth is sufficient for everyone's need, but not everyone's greed." And everyone is the key word here. Thank you.